Okay, let's go ahead and take a look at the common ion effect that happens in equilibrium. Okay, so in the graphic below, you see that on the left, right, we have a solution that is made up of strontium oxalate put into water, and the solution becomes saturated. Now, what is saturated? Saturated means that a solution has so much solute that the solvent can no longer dissolve it. And whatever remains undissolved will kind of pool at the bottom, like here, like you see in the graphic. So the strontium oxalate has been dissolved, but it's gotten so much that the solution has become saturated and can no longer dissolve anymore. You'll see that in the graphic when you see this kind of at the bottom of the container here. The best way to think about this is if you're having a cup of iced tea or a glass of iced tea, you add too much sugar and the sugar kind of sits at the bottom. What's happened is that tea has become saturated. It can no longer dissolve the sugar, and the sugar kind of sits at the bottom. So that's what we see here. Now, we have a saturated solution of the strontium oxalate, and what we're going to do is we're going to add sodium oxalate, okay, to the solution. Now, sodium oxalate, if you can see, has an ion that in common with the first solute, right? That ion is the oxalate ion here, right? So this ion is in common with this ion. So because those are the same ions, we call this the common ion. Now, common ion, okay? Now, when you add another source of an ion that's already in solution, then that actually has an effect of changing the solubility of the solution. So because it changes the solubility, we call this the common ion effect. So let's take a look at the vat on the right. We've added the source of sodium oxalate to the solution, right? And as you can see, we have much more oxalate ions in solution now. So as this happens, because we have more oxalate in the solution, then we begin to increase the number of collisions between the oxalate and the strontium. And as this happens, these two guys begin to reform, and you begin to actually see more strontium oxalate reform into solution, causing it to decrease the solubility, right? So remember, the solution already had plenty of source or plenty amount of oxalate, and what we did was we added more. So as a result of adding more, you begin to reform those ions and more solid begins to form. So the moral of the story here is the common ion effect actually lessens or decreases the molar solubility. All right, it decreases the molar solubility. Now, as you add more of the solute or more of the same ion, right, then what happens is you begin to shift the equilibrium, right? You shift the equilibrium. All right. And as you shift the equilibrium, in this case, what's happening is we're reforming this compound. So you're shifting the equilibrium to the reactants. Right? So we're going to take a look at a problem here that's going to help us understand how this works. Okay? Let's take a look at a reaction and see how the common ion effect plays a role in solubility. The question says, what is the molar solubility of lead iodide in a 0.1 molar solution of sodium iodide? For the PbI2 or the lead 2 iodide, the KSP is 7.9 times 10 to the negative 9. So we're going to do this in a couple of ways. We're going to do it one without the common ion, and then we're going to do it again with the common ion so you can see that effect that it has on the molar solubility. So first things first, okay, is I'm going to go ahead and write the balanced chemical equation, all right, so we can see exactly what's going on here. So lead iodide is dissolving into lead 2, that goes into an aqueous environment, right, plus 2I1, this is also in solution, okay. Now, remember, we're not decomposing the molecule. We're simply separating the ions. So what that does is it creates iodine ions. Don't fall into the trap of, well, it's splitting apart. I know that iodine is diatomic, and then you write this as iodine 2 or I2. That's incorrect because, again, you're not breaking bonds. You're not decomposing the molecule, right? You're simply dissolving and separating the ions, dissociating the ions, okay? Okay, so here is our reaction. Now, if we're going to set this up, right, we're going to set it up with our ice chart. Okay. Remember that when you're working with solubility products, the solid one is not included, so we don't have to worry about that one. Our focus is going to be over here. Okay. Now, if we're calculating the solubility product, right, we know that at the beginning of the reaction or before the solution takes place. Sorry, I froze up there for a second. We know that the initial concentration here is going to be 0. 0, 0. Okay? Now, the change in concentration is going to happen as x. Remember, this comes from the coefficients in the equation, and this is going to be a plus 2x. Okay? If we add these together, this becomes x, this becomes 2x. Okay? And then we can write the solubility constant, okay? So if I was to write the mass action equation, right, here's what it would look like. It would say that KSP is equal to the molar solubility, right, concentration of lead 2 plus and iodine minus, again, in solution, squared. Okay? So that's our KSP. Remember, the solid has no change in concentration, so it is not included in our mass action equation. Okay, so now we know what our variables are for the mass action equation. So we would write this as KSP is equal to x times 2x squared, right? We know the value of our KSP. Our KSP is equal to 7.9 times 10 to the negative 9. That's going to be equal to x times 4x squared. Whoops. Okay, if you multiply those together, we get 7.9 times 10 to the negative 9 is equal to 4x cubed, right? Again, from here, it's just algebra, right? We're going to take our 7.9 times 10 to the negative 9, right? Set that equal to 4x cubed. Divide, sorry guys, I don't know why that keeps popping up. Divide by 4, okay? That equals 8.0 times 10 to the negative 9. Okay, that's going to be equal to x cubed. And then if I take the cube root of both sides, I end up with 1.99 times 10 to the negative 3. Okay, so this is, sorry, I put the M there. This is the molar solubility of lead iodide in pure water without the addition of a common ion, right, which is the iodine. Okay, so this is our review, right? We should know how to do this. Now, what we're going to do now is we're going to do the same process, but now we're going to see what role this guy has in the solution, right? We're going to add 0.10 molar solution of NaI, and we're going to see how that changes the solubility of the lead iodide, okay? So again, it's the same chemical reaction, okay? We're going to start right here. It's lead iodide That's not going to change, right? It goes to equilibrium to produce lead 2 plus in solution, okay, plus 2 iodine in solution, okay? Now, what we got to understand here is that this is 0.10 molar, okay? So 0.10 molar of sodium iodide tells us a couple things, right? So I know that lead iodide, 0.10 molar of sodium iodide has a 1-to-1 ratio. So what this tells me is that I'm going to add 0.110 molar of sodium, and I'm going to add the same amount of iodine, right? So this is going to be what's added to the solution. When we set up our ice table for this reaction, okay, we're going to take a look. Again, lead iodide is not included, but here's where it changes, all right? When I do the initial concentration, the lead still has a zero initial concentration because we're not adding more lead with the sodium iodide. What's going to change is the amount of the initial iodine, right? So here, we're going to include the 0.10 of the iodide from the common ion. Okay, so this is going to be in addition to whatever iodine is in the solution from the lead iodide. So this is where it changes right here. We're going to add this to the initial. Okay, now the change, everything else should stay the same. So this is going to be plus X, and this is going to be plus 2X. Remember, the 2 comes from this guy right here. Okay, now at equilibrium, here's where we're at. We're going to be with X, and then this is going to be the 0.10 plus that 2x, right? Because remember, the equilibrium is this plus this, right? So this is where we're at. Now, this kind of looks a little bit complicated, but here's what you need to remember, okay? Take a look at this value here for the KSP, okay? It's -9, right? So if I was to write this as an expanded form, right? So 7.9 times 10 to the -9. And if I was to write that in expanded form, that's going to look like this. Okay. I'm going to add one extra 0. Okay, it's going to look like this. So even if, right, we have this 2x, right, all those changes are going to occur back here, right? They're going to occur back here. As you can see, this number is really like right around here, okay? So because the 2x changes are happening way, way beyond our significant figures, and it's like way, way down in the zeros, it's actually a really, really small amount. So because it's a really, really small amount, right, then we can kind of neglect this. This is negligible because the amount that it's going to affect this number is going to be very, very small, and it's going to be beyond our level of precision, right? Because here you can see that we're at, 2 significant figures, and we're really, really close to the 0. And when we look at expanded form, whatever changes these 2x are going to happen, they're going to happen way back here. And that's not going to affect the values up here. So because of that, we can find that 2x is negligible, right? So if we decide, right, or assume that 2x is negligible, then we can write this as x and then just 0.10, right? We don't have to include the 2x. Right. Now, if we were to write our mass action equation, it'd be exactly the same. KSP is equal to the concentration of the lead 2 plus and the concentration of the iodine 1 minus, and this is going to be squared, right? So let's replace these then. What we end up with then is going to be x times 0.10 is equal to the KSP, which is 7.9 times 10 to the negative 9. Okay? From here, this is squared, by the way, sorry. From here, then we just got to do the algebra, right? So if I take 0.01, or 0.10, sorry, and I square that, all right, here's where I end up. I end up at 0.01, all right, x is equal to 7.9 times 10 to the negative 9, okay? Then from here, all I got to do is divide. Okay? I end up at 7.9 times 10 to the negative 7. Okay? Now, this is what's happened to the solubility compared to not adding more of the common ion. So let's take a look at our original calculation. Okay? We were here. So in pure water, we ended up at 1.9. Let me do this in a different color here. 1.99 times 10 to the negative 3 compared to 7.9 times 10 to the negative 7. So you can see, right, that the molar solubility has decreased from pure water to common ion addition. Because the molar solubility has decreased, then what happens, right, is the equilibrium is shifted, right? The equilibrium is now shifted toward the reactants, and it's producing more of the original reactant. So if we were to take a look at these two comparisons, right, the best way to show this is that this is greater than this, right? By adding more of the common ion, right, you've decreased molar solubility, because remember, this number is greater than 7.9, or 1.99 times 10 to the negative 3 is greater than 7.9 times 10 to the negative 7. So by decreasing the solubility, you've increased the amount of solid, or the amount of undissolved, right, reactant in that solution. So the common ion effect, right, what it does, it shifts the equilibrium back to the reactants, and this begins to reform, right? And that's the difference. That's the difference. Now, we're going to do this problem in class today. So I want you to take a minute, and I want you to pause the video, write it down, and have it ready to go.